Okay, let's jump into chapter 6. Our applications, an area between curves, and velocity and net change. Because most of y'all are taking a calculus class not because you're a math major, but because you probably got to take some physics. And that's why we mess around with calculus for the most part. Unlike us math people where we just do it to do it, you're probably going to use it. And this will most certainly show up in your physics classes. So let's get to it. Now we're going to begin with a definition. Position, velocity, displacement, and distance. So we have the position of an object moving along a line at time t. So S of t is our position function. And it's talking about the location relative to its origin. The velocity is the derivative of the position function. And if you took a derivative on velocity, you'd get the acceleration function. Moving on. Now, we need to know the difference between displacement and distance traveled, 3 and 4. Displacement, well, that has like a positive and a negative. So let me just think of it this way. Let me yank it aside. We're going to go on just, let's say we start right here. Right there at 0. And I'm going to give you the same things. If you ever watch me teach in class, if you ever get that, watch a spaz do it, I will pace back and forth. Now we know that this is the positive over here. That's the positive. And this is the negative direction. So if you were to walk and go back and forth, back and forth, back and forth, back and forth, and end up right here, right back to the same position, well, the position function, or displacement, well, the displacement is 0. You didn't go anywhere. Maybe moved around, paced back and forth, but you didn't go anywhere. But the distance, heck yeah, you move some distance. Anybody got one of those little watches you put on, tells you how far you walk? It doesn't matter. It's telling you the distance, not the displacement. Now, here's a terrible way that they describe it. So displacement is beautiful when it comes to taking integrals. It's all in there. As long as you have a velocity function, you take an integral on a velocity function from some time to some other time. It's just taking the integral. It's just taking the integral. It's very, very straightforward. You just take it, go, plug it in, and you end up with this. Now, distance traveled by the object. Now, that's more challenging. And this right here, I'd throw this out. It makes it seem like it's very simple. It's not very simple. It's the tougher part. It says it's just the absolute value of the velocity function. Because distance traveled has no sign. It's always positive. You never travel a negative distance. You only travel a positive distance. Well, let's see a problem. Enough of me babbling on. Let's see a problem. So this is straight from your textbook. If you're to look up how to solve any of these, this is probably the one that's going to come up. And maybe I can help walk you through it. All right, displacement from velocity. A jogger runs along a straight road with velocity in miles an hour. This is equal to 2t squared minus 8t plus 6 for 3 hours. Oh, dude, you're jogging for 3 hours. What a wacky dude. All right, so it says graph the velocity function over the interval 0 to... Okay, cool. We got this. So we want to graph this thing out now. I am the best at graphing. I'm telling you. I am the best. You will get to laugh at me quite a bit. So let's take our velocity function. This is our y. This is our t. And I'm saying y is equal to v of t, which is 2t squared minus 8t plus 6. So I decided, you know what? Let's yank that thing out. Let's factor it up. Oh, there we go. So it's some sort of parabola. It's facing up, and it's got intercepts. It's 1 and 3. So we have some sort of parabola. Let's call this 6. it takes off like that. So what this means is we have a positive displacement here, but we're also going to have a negative displacement down here. Be going the other direction. So the jogger ran, say, north for the first hour, and then turned around and traveled south for the next 2 hours. So we've graphed it. It's not beautiful, but it's something, huh? Okay. Now it says find the displacement of the jogger in miles on the time interval from 0 to 1, 1 to 3, and 0 to 3. And this is actually going to help us out quite a bit. Quite a bit. So let's do part B. It says, all right, so from 0 to 1. That means it's the, S of t is going to be from 0 to 1 of our 2t squared minus 8t plus 6 dt. So let's go find an antiderivative on this. So we're going to get, what is that, 2/3 t cubed minus 4t squared. Sorry, I'm jumping past the algebra, but I assume you can do algebra, can't you? So we're going from 0 to 1. No biggie, so we're going to get 2/3 1 cubed minus 4 times 1 squared plus 6 times 1. There's our upper bound. And then we're going to subtract out our 2/3 times 0 minus 4 times 0. Oh, squared. This is cubed. Oh, I'm sorry. Plus 6 times 0. Zeros are the best. It's just 0. So we ended up with 2/3 minus 4 plus 6. What's that? 2 plus 2/3. So what do we got? 6/3 plus 2/3 is equal to 8/3. But we got to give it units. That was in velocity. That was in miles an hour. So this is just saying, how far did dude travel? 8/3 of a mile. Huh? 8/3 of a mile. No biggie. Next, we want to do it from, where's the next one? From 1 to 3. Now, we would not solve in this manner, so let's go find our next one. From 1 to 3. We're going to plug all this nonsense back in again, so it's 2/3 t, no it's not. Sorry about that. So 2t squared minus 8t plus 6 dt. And we still end up with 2/3 t cubed minus 4t squared plus 6t. But now we're evaluating from 1 to 3. All right, so we're going to get 2/3 times 3 cubed minus 4 times 3 squared plus 6 times 3. And then we're going to subtract out our from 1, and that's 8/3. I'll let you think about why that's just 8/3 for the 1 that we've already solved for. Just saving some time. So we're going to get 27 divided by 3, 2 times 9, that's 18. 4 times 9 is 36. Plus 18. Huh. Minus 8/3. So this ends up being minus 8/3 of a mile. Okay. Let's go. And then when we go from 0 to 3, well, shoot, I'm not doing another frickin' from 0 to 3 of our velocity function. Sorry, I'm cheating at this point. I'm not going to write all that out. That's the same thing as from 0 to 1 of our velocity function. And then our from 1 to 3 of our velocity function. And we already found those. That's 8/3 plus negative 8/3. So his displacement was 0 miles. Oh. So dude jogged north. Then turned around and just jogged south back home. And I guess just took him a lot longer to go there. Now lastly, it wants us to find what is the distance traveled. And it tells us that, okay, well, it's from 0 to 3 of the absolute value of our velocity function. This does nothing for us. This is garbage. But what we can do, let's look right up above. From 0 to 1, we knew it was positive. From 1 to 3, we knew this was negative, but we can only have the absolute value. So I got to jump back up to the top and show you, hey, look at this. Our distance traveled would actually look like this. Boom. And then all of it would be positive. So all we have to do is find where the intercepts are. Anything that's in the negative region, we're just going to give it a positive. So the total distance traveled would be the absolute value of 8/3 from up here, plus the absolute value of negative 8/3, and that's equal to positive 16/3 miles. I don't think I did a very good job of explaining this, but we'll do another one. We'll see it. But that's how we're going to do this. So displacement has sign to it. Distance is always positive. You have to find out where those intercepts lie and make certain that we're only taking the positive region when doing distance. Distance is a pain in the butt. So there's your intro. We'll do another one next.